Hello and welcome back everyone. And geometry today, we will be going over what is known as the basic proportionality theorem. But at the same time, what we're going to do is transition to a different textbooks just to make things a little bit easier because you're going to be doing a lot more of the algebra stuff, and it's going to be good to be able to kind of blend in the algebra and also geometry together, so then that way you can kind of see each of those work hand in hand rather than just doing all the proof the entire time. So anyhow, let's go ahead and get started. As I mentioned, this section is on what is known as the basic proportionality theorem. And another name for it is actually called the AA similarity, and I will explain why is that in just a little bit. So here is going to be our first theorem, which will be used to prove something that is bigger right after this. So in a way, this is going to be what is known as a kind of a lemma, because we don't really use this theorem that much, but instead we use the theorem that comes afterwards. So anyhow, here's the scenario then. Given that you have a triangle ABC where D is in between A and B, E is in between A and C, and finally DE is parallel to BC. So you can see the picture on the right hand side that you have that triangle, and DE is a segment that is basically inside the triangle such that it is parallel to the third side. What I want to do is that if that's the case, I want to prove that AD over DB is equal to AE over EC. And in addition to that, AE over AB is equal to AD over AB is equal to AE over AC. So that is to say, looking at in terms of sides, AD is located over here. This side over here, AD, divided by this side over here is equivalent to this side over here divided by this side over here. I think by drawing those dots, that might be a little bit easier to look at. Whereas the second step, I want to prove that if I have that in addition, I can prove that AD, which is that red dot once again, if I divide that by the entire length of AB, that is equivalent to AE, which is this piece right here. And then I can divide that by the entire length of AC over here. So this one is going to be a little bit more flexible in that case. But anyhow, let's go ahead and start and see how this actually works out then. Okay, so in terms of the proof, what I'm going to do is I'm going to take my triangle that I have, and I'm going to introduce a segment BE. And then I'm also going to introduce a segment CD. And what that's going to do is we're going to break that into two different triangles, as you can see right below. In each case, what I will do is find the ratio of their two areas. So the top triangle is going to be ADE, which is going to be this guy over here. And I am going to also find the area of the other triangle that's right underneath it, which is going to be DBE over here. Okay. Now, since these two triangles are connected to each other by DE, then what that means is if I look at their altitude, they have the same altitude. And let me go ahead and draw that in there over here. So that H right there is going to be their altitude. So the area of the top triangle is going to be 1/2 multiplied by the height multiplied by AD. Then divided by the bottom triangle, it's going to be 1/2 multiplied by the height, which is also going to be h, because again, these two triangles share the same altitude, multiplied by its respective base, which is going to be dB. So you can see that the 1/2 cancels out, the h cancels out. So the ratio of their sides are going to be the ratio of the base, which is AD divided by dB. Then for the other triangle on the right hand side, I'm going to do something similar. I'm going to do something identical, if anything. I'm going to go ahead and take the area of this top triangle and then divide it by the area of the bottom triangle to get a proportional ratio. And with that set up, it's basically the same idea as what's on the left. So this is going to give us AE divided by EC. So there it is. If you notice, AD divided by DB, that is going to be this piece over here, whereas AE divided by EC, that's going to be this piece over there. Now, looking at each of these proportionality, you'll notice that the top right here, that is the same thing for both of them. They both have the area of ADE. So that means that I can almost set them equal to each other. The problem that is going to be problematic is that the bottom triangle, well, we don't know if they're the same or not, because one is saying BDE, the other one is saying CED. So if we can show that those two triangles are the same on the bottom or congruent, then that means that they have the same area, then therefore I can set them equal to each other. Well, fortunately, they are actually going to be congruent to each other, because if you look at the picture right below it, there is each respective triangle. First, we have BDE, which is over here, and then we also have DEC, which is over here right next to it. Note that, remember, DE is parallel to the side that's on the bottom, BC. So what that means is they share the same base, because DE is the same base for each one of them. Then you also have the height right here for one of them, which is the same as the height for the other one. Because if I go back to the other triangle, you'll notice that these two lengths right here, this length and this length, both are heights. They're going to be the same thing. So if they both have the same base and they both have the same height, then that means that the area of triangle BDE will then be equal to the area of triangle CED. So then what that means is these two right here are actually equal to each other, because the bottom area is actually the same as the bottom area over here on the right. And the top is the same, well, because they're both the same thing. So in the end, then that means now I can go ahead and set them equal to each other. AD over DB is equal to AE over EC. Now, if this is a whole bunch of variables and you're wondering, okay, well, what's the point of all of this? Well, here, let me just go ahead and draw a picture for you then, just so you can see it a little bit better. So let's say that we have a triangle where, like we said, these two sides right here are parallel to each other as in setup. Let's say in addition to that, this is going to be 2 right here, a length of 2, and this right here is going to be a length of 1. And let's say for the time being, I'm going to go ahead and tell you that this is going to be a length of 4. So the question then is, what is the length of this piece over here that's on the bottom? Well, according to this proportionality, we can set up the following now. 2 divided by 1, 2 divided by 1 is equal to 4 divided by x, 4 divided by x. And now we can go ahead and solve for the missing sides. So 2x is equal to 4 times 1 because of cross multiplying. So x is equal to 2. So that's the benefit of having to solve for this piece right here. Okay. Now you'll notice that in our proof, we can go a little bit further. We can actually say that AD divided by AB is equal to AE divided by AC, meaning that I can look at the top sides right here divided by the whole side on the side over here. So what we need to do is we need to somehow modify our equation to show that this right here leads into this right here. Well, that's actually not too bad then, because all we have to do is just do kind of like a quick extension then. If I take the bottom part right here, dB, what I'm going to do is I'm going to go ahead and add on to it then, okay? So let me see if I can kind of show that up here for the time being. First off, taking what we have, okay, sorry, looks like I'm going to be running out of space right here. So I'm going to go ahead and erase some of this stuff just to give myself a little bit more room, okay? So hopefully we don't need this anymore. And, well, if I need it, then I am going to be in trouble, okay? All right, so let's do this. Let me go ahead and I am going to go ahead and substitute, okay? I'm going to go ahead and substitute each of the following sides in terms of variables, so then that way you can see it a little bit better, okay? Let me go ahead and call this x, let me go ahead and call this y, let me go ahead and call this a, let me go ahead and call this b. So that is going to be my setup for the time being, okay? According to what I proved so far, I have shown that x over a is equal to y over b. Okay, so that's what I've proved so far. What I need to show is the next step to take a little bit further and say that if I have x over x plus a, then that is going to be equal to y over y plus b, just to make this a little bit more lengthier or stronger in this case. Okay, so I need to be given on the left, I need to prove what I have on the right algebraically. Well, the best thing I can do is, first of all, let me go ahead and flip the fraction then. So I'm going to go ahead and say a over x is equal to b over y, the reciprocals of both sides then. Then after that, I am going to go ahead and add consistency to both sides. Let's see. Why don't I go ahead and add a plus x. Actually, oh, I see what's happening. Let me go ahead and clean that up a little bit. Sorry about that. I know what I'm supposed to add now. I'm going to go ahead and add 1 to both sides. That's right. So it's going to look something like this. Okay. If I add 1 to both sides, now I can go ahead and get a common denominator out of all of them. So a over x plus x over x is equal to b over y plus y over y. And if I take what I have right here and clean it up a little bit more, we have a over x divided by x is equal to b plus y divided by y. And if I now take the reciprocal of both sides, now we can actually have that proportionality that we said from earlier. So what that means is now if I go back to my example over here, we can do the following. We can say 2, which is this length over here, divided by the entire length right here, which is 2 plus 1 is equal to 3, should also be equal to 4, which is the opposite length over here, divided by the entire length over here of 4 plus x. And this is also another way to solve for x then. Okay, so this will allow you to be a little bit more versatile when it comes to your proportionality. But anyhow, what I need to do now is I need to take this and prove something that is going to be more useful, and you're going to be seeing quite a bit of this actually from here on out. This is what is known as the AAA similarity, and we kind of talked about this a little bit in the last section or a couple of sections ago. It says that if you have 2 triangles where all the angles are congruent to each other, so here we have one angle in one triangle is congruent to another, and then the second angle is congruent to the second angle in the other triangle, and the third one is congruent to the third angle in the other triangle, then it turns out that these 2 triangles are going to be proportional to each other. Okay, more specifically, you can say that they are similar to each other. So what I need to do is I need to prove that that's true. ABC, the triangle, is similar to triangle DEF. And by similarity, what that means is I need to show that I can set up the following ratio. AB over DE is equal to AC over DF, and then that is equal to BC over EF. Okay. Sure, let's just go ahead and see if we can dive into it then. Okay. Now, the trick that is going to make this a little bit easier, or how I'm going to implement the other previous problem, is that I'm going to actually overlap the 2 triangles together, okay? Notice that in this picture, we said that angle A is congruent to angle D. So what that means is I can draw it so then that way we have one triangle, which is the bigger one, DEF, is going to absorb the smaller one, which is going to be A, B, C, like this. So you can see how they are kind of like absorbed together to get one whole triangle as a result. Well, keep in mind that angle B over here is congruent to angle E down there. Angle F over there on the right is congruent to angle C over there on the right. So if you look at the pictures, you can see that those 2 triangles right there, because of my angle setup, then that means that BC has to be parallel to EF. Okay, so BC has to be parallel to EF, and the reason for that is that because we have corresponding angles that will tell us that the sides are going to be parallel. So CAP, if you remember then. Okay, and as soon as we have that, then that means that we can use the previous theorem. Then by theorem 12, I think it was like 2, which is the previous one, then we can say the following. AB divided by DE is equal to AC divided by DF. And hey, there you go. Now we have this part right here is going to be equal to this second part over here. And if you're wondering how we're going to get the third part into the mix, well, all I have to do is I can take the triangles and rotate it, and so that my triangle would look something like this. So here you still have the 2 triangles overlapping, but it looks like the following. And then we can set up another proportionality to get BC is equal to, BC divided by EF in there. And all of them are going to be congruent to each other then. Okay, or sorry, similar to each other. All right, so there it is. Those are going to be the theorem right here. And this theorem, you'll notice that, again, I called it AAA similarity, meaning that if all three angles are congruent to each other, then this is going to be true. This is kind of like, congruency, but for similar triangle. The one other thing that I need to mention is that we don't really need to have all three angles to be similar to each other, to be congruent to each other. We can have it such that two angles are similar to each other, are congruent to each other. So that is to say, if you know that A is congruent to D and B is congruent to E, that is sufficient, because remember that inside a triangle, the sum of all the interior angle adds up to be 180. So that forces C to be congruent to F. So really, we don't really need that last part. And hence, that's why we call it AA similarity instead of AAA similarity, because it's going to be less work. But anyhow, let's go ahead and try to look at this as a problem so you can see how this actually works out. So here is an example of it that's algebraic, okay? So in this picture, you can see that we have a triangle inside a triangle where we have two sides that are going to be parallel to each other. So according to my theorem 12-2, or we can use the AA similarity, we can set up the following proportionality. We can say 15 over 10 is equal to 9 over x. Or if you want, you can say 15 over 25, because that 25 right here is the sum of this guy and this guy put together, which is going to be 25, is equal to 9 divided by x plus 9. So if you can solve for either one of these ratios, then that means you can figure out what x is going to be. I'm going to go ahead and take the one that's on the bottom because, because I can't work off the one on the top since there's no space. So we're going to go ahead and clean this up. So 15 multiplied by x plus 9 is equal to 9 multiplied by 25. And to avoid multiplying things out, I'm going to go ahead and reduce. 15 and 25, they go divide each other. They can both be divided by 5. So that'll give me 3 over here, and that'll give me 5 over here. So 9 times 5, that's equal to 45. And 3 multiplied by x, that gives me 3x. 3 times 9, that gives me 27. So subtract that 27 from both sides. 45 minus 27, that's equal to 18. So it looks like x is going to be equal to 6, which is over here then. Okay. And, we'll go ahead and throw 6 into this one just to make sure that it works out. So let's see if this fraction is true. 15 over 10 is reduced to 3 over 2, which definitely looks like it's going to be 9 over 6, because they can then be reduced to 3 over 2 also. So that works out, okay? Now, let's look at this as a proof, and I think that'll probably do it then. Okay, so this time, let's say that we have the triangle such that we're given the following information. EF is parallel to RS. So you can see that in the picture. I drew the triangle to represent that they're parallel. What I want to do is part A, I want to prove that the triangles are going to be similar. Well, that's probably going to be the easier part. The second part is to prove that we have this equation, which is true. Fx times Rs is equal to Sx times Rs. So we'll save that part for a little bit later, but let's go ahead and dive into part A first. How can we show that those two triangles are going to be similar? Well, I think the best way we can do this is probably use the AA similarity, because that's the only thing that we can have to work off of. Okay, look at those two triangles, XEF, and also triangle, let me see if I can kind of isolate, XRS, okay? Note that both triangles, they share this angle, which is angle X. Then if I can somehow show that this angle is going to be congruent to this angle, I think we're pretty much done, because then we can use your AA similarity. And I think they are going to be congruent to each other because of PCA. The sides are parallel, so therefore their corresponding angles are going to be congruent to each other. So let's go ahead and look at this as a proof then. We can say angle X is going to be congruent to angle X by reflexive. Okay. Then we can say that angle XEF is going to be congruent to angle XRS because by PCA, right? Because this, the sides are going to be parallel, so therefore their corresponding angles are going to be congruent to each other. So now we can go ahead and say triangle FX, sorry. Oh, no wonder I wrote it wrong. That's probably why. FEX. So let me go ahead and kind of sneak that in there. FEX over here. Okay. So the triangle FEX is going to be similar to triangle SRX then, as a result. Okay. And the reason for that is going to be by AA similarity. Okay. All right. So now that is going to be part A, which is very straightforward for the most part, hopefully. Now let's